Good morning, everybody. In today's lecture, we are going to talk about soil classification for engineering purposes. While soil description involves the details of material and mass properties, soil classification allocates a soil to a group on the basis of particle size and plasticity. Even though several classification systems are now in use, none of them is totally definitive of any soil for all possible applications due to the wide diversity of soil properties. The question is, what system shall we use then? Since geotechnical engineers generally go for the Unified Soil Classification System, USCS in short, the guidelines for classifying soil with respect to USCS will be discussed in detail. Furthermore, the difference between them appears to be rather negligible. The USCS classifies soils into two broad categories. The first category are the coarse grained soils. They are gravelly and sandy in nature, with less than 50% passing through the No 200 sieve. Now, if the percent retained on the No 200 sieve is more than 50%, then you need to move to the second column, where you need to check if the percentage retained on the No 4 sieve is more than 50% or less than 50%. Depending on your choice, then you need to move to the third column where you need to check if the percentage passing the No 200 sieve is in between these values. Now, again, depending on your choice, you need to move to the fourth column. There, you need to check Cu, Cc values and the Pi values. Cc and Cu values are the grading characteristics obtained from the particle size distribution of soil. Pi is the plasticity index. Don't worry about the unknowns at the moment. They will be clearly explained on the following pages. Now, again here, based on your choice, you need to move to the fourth column to choose symbol to represent your soil with the group names explained here. The second category are the fine-grained soils. They are with 50% or more passing through the No 200 sieve. Now, if the percentage passing the No 200 sieve is more than 50%, you need to move to the second column. And there you need to check whether liquid limit is greater than 50% or not. Depending on your answer, you need to move to the third column where you need to check if the Pi value, plasticity index, is greater than A line or not. A line is an arbitrary division between clays and silts given in the plasticity chart. As I said earlier, don't worry about the unknowns. They will be clear on the following pages. Now, here, depending on your choice, you need to move to the fourth column to choose symbol to represent your soil with the group names explained in the final column. Symbols used for the classification are OML, which is organic matter loss, CC, coefficient of curvature, Cu, coefficient of uniformity, PT is pit, highly organic soil. LL, liquid limit, PI, as explained, plasticity index, G, gravel, S, sand, C stand for clay, M stands for silt, W well graded, P poorly graded, L low plasticity if the liquid limit is less than 50, H high plasticity is if the liquid limit greater than 50, O is the organic matter. The plasticity chart referred to in USCS is given in the figure here. For fine-grained soils, plasticity seems to be the most important property because it controls the soil behavior. For that reason, such soils are classified depending on their plasticity using the plasticity chart. In this chart, the A line, which is the yellow line in the figure, defines the type of soil. All soils above the A line are classified as clay soil, while soils below the A line are considered to be silt. U line, the red line in the figure, is not used in soil classification, but it is the upper boundary of your test results for natural soils. If your test results are above U line, it means that they are mistaken, so you need to repeat them. Your test results should be in between U line and A line. For the engineering classification with respect to unified soil classification system, some or all of the following information must be known. Gravel percent, that is the portion passing the 76.2 millimeter sieve and retained on the 4.75 millimeter sieve. Sand percent, that is the fraction passing the 4.75 millimeter sieve and retained on the 0.075 millimeter sieve, which is the no 200 sieve. Silt and clay percent, that is the portion finer than the 0.075 millimeter sieve. Coefficient of uniformity and coefficient of curvature. As explained earlier, these are the grading characteristics obtained from the particle size distribution curve of soil. And finally, liquid limit and plasticity index of the portion of soil passing the 0.425 millimeter sieve, which is the no 40 sieve. For the particle size determination of coarse-grained soil, the method is sieve analysis. A representative oven-dried soil sample is sifted through a nest of standard test sieves formed in descending order of mesh size. A pan is placed below the bottom sieve to gather the soil passing the finest sieve. So, by measuring the mass of soil held in each mesh and expressing it as a percentage of the total, the grain size distribution curve of coarse-grained soil is obtained. For the particle size determination of fine-grained fraction of soil mass, the method is hydrometer. Hydrometer analysis is based on Stokes' law. Recall that in a suspension, the coarse particles settle first, followed by the finer particles as illustrated in the figures here. The hydrometer, which is shown here, is calibrated to read the specific gravity of soil particles around the bulb in suspension. After the start of sedimentation at time t, soil particles in suspension at depth L will have diameters smaller than those calculated by this equation, in which rho sub W is the density of water, nu is the viscosity of water, d is the diameter of soil particles, and Gs is the specific gravity of soil solids. This test is not frequently used. It is only required when the soil contains more than 10% fineness. Thereafter, the percentage of the particles finer than D is calculated as a ratio between the weight of solids per mil at depth L after T time and the weight of solids per mil in original suspension. Now you may ask yourselves why we can't use the sieve test to determine the amount of silt and clay instead of hydrometer test. Well, the sieve test does not work for the fine material because the size of fine particles is too small, which makes it extremely difficult to manufacture sieves with the meshes finer than 0.075 millimeter opening. In addition, smaller clay particles tend to clog and cannot pass through the meshes individually. After all, the results of sieve analysis and the hydrometer analysis are combined on one graph to present particle size distribution curve for a given soil mass. To determine soil gradation, it is essential to obtain the curvature and the uniformity coefficients which are associated with certain points on the gradation curve. C sub C is the ratio between d sub 30 squared and d sub 10 times d sub 60. C sub U, on the other hand, is the ratio between d sub 60 and d sub 10. D sub 10, d sub 30, and d sub 60 are referred to the particle sizes that are finer than 10%, 30%, and 60% as illustrated in the figure. Now, for coarse-grained soil to be well graded, the criteria given in brackets for gravel and for sand must be satisfied. Otherwise, the soil is considered to be poorly graded. For good reason, you may ask what the poorly graded or well-graded soil is. Well-graded soils, as depicted here and represented with Q1 in the figure, include a wide range of soil particles. Poorly graded soils, on the other hand, as illustrated here and represented with Q3 in the figure, don't have all particle sizes. Their particle sizes are more or less the same. That's why they are also called uniformly graded soil, or they can have at least one particle size missing, as depicted here and represented with curve 2 in the figure. By the way, well-graded soils typically have greater densities than poorly graded ones. Another question is, can we use the same approach of soil gradation for fine-grained soils? No, we cannot, because the plasticity of fine-grained soils has a meaningful influence on engineering properties such as shear strength and compressibility. Plastic consistency is used as a basis for their classification. 4 consistency states may be defined for cohesive soils as illustrated in the figure. Solid state, semi-plastic solid state, plastic state, and liquid state. Now then, liquid limit as the water content where the soil begins to act like a liquid. Plastic limit as the water content at which soil shifts its state from semi-solid to plastic state. And finally, shrinkage limit is the moisture content where the soil turns into solid state. The two most important of these consistencies are the liquid and plastic limits, because they represent the upper and lower boundaries of the plastic state. In addition, the range of plastic state is defined by their difference and is called the plasticity index. The relationship between plasticity index and the liquid limit is used in the plasticity chart of Unified Soil Classification System as explained earlier to define whether a fine-grained soil is a clay or a silt of low, high, or medium plasticity. Now, to determine the plastic and liquid limits, Atterberg's tests are performed. Let us see what they are. The liquid limit test includes mixing soil with different amount of water and determining its consistency using a liquid limit device. The liquid limit test can be carried out by means of 2 different devices, namely the Casagrande device and the liquid limit penetrometer device. Since the Casagrande device is well known and widely used in the laboratories, I will give you a brief information about it. The details of the test can be found in any related books and manuals. And you will have also an exercise in the laboratory. In this test, moist soil is placed in the cap of the liquid limit device, as shown here, and a groove is cut on the middle of the soil sample. By turning the crank on the device, the cap will drop from a height of 10 millimeter, and the soil on both sides will move towards each other, closing the groove. The number of blows required to close the groove over a length of about 13 millimeter and the moisture content corresponding to this state are recorded. The procedure should be repeated at least 3 times to obtain a range of blow counts, and the results are presented as a relation between moisture content and the number of blows as shown in the figure here. The liquid limit is then determined as the moisture content corresponding to the 25 volts. The plastic limit test is considered to be awkward and unpleasant because it requires experience and a lot of patience. This test is carried out by taking about 10 grams of soil paste prepared for liquid limit test and rolling it into a bowl. Then the bowl is rolled on a glass sheet as shown in the figure to form a thread of soil using the palm and the fingers with light pressure. You shouldn't apply high pressure, otherwise your samples will be crushed. The rolling is continued until the diameter of the thread reaches about 3 millimeter, as illustrated in the figure here. Now at this stage, if there is no crack on the surface or no crumble, then the soil is reformed into a ball and it is re-rolled on the glass sheet again. The procedure of rolling and re-rolling is continued until the thread begins to crumble at 3 millimeter in diameter. At this stage, the moisture content of soil is defined as plastic limit. The test should be repeated at least 3 times and an average value of plastic limit is recorded or should be recorded accordingly. Consistency limit values. In other words, Atterberg limit values for some clay minerals are given in the table here. If you notice, montmorillonite has the greatest liquid limit, followed by attapulgite. Type of clay minerals and their comparable amounts in a soil will influence the liquid and plastic limits. Fine-grained soils can also be classified based on their activity. Activity is defined as the ratio of the plasticity index to the percentage of clay fraction as formulated here. The classification of soils based on the activity is given in the table here. If the activity value is less than 0.75, clays are considered to be inactive. However, if the activity is greater than 2, clays are considered to be highly active. Activities of some known clay minerals are also given in the table here. If you notice, smectite has the greatest value, activity value, among others. From all these, we understand that the more active the fine-grained soil is, the more problem it will presumably cause during construction. The liquidity index is also used for soil classification. It shows the consistency of fine-grained soils. It is related to the soil liquid and plastic limits as well as the in situ water content. In the table here, you see the soil classification based on liquidity index. For example, if liquidity index is less than 0, when the soil sheared, it will show brittle fracture. However, if the liquidity index is greater than 1, if the soil is sheared, it will behave as a viscous liquid. Now, Soils with liquidity index greater than 1 will probably cause significant problems during construction. For many naturally deposited clay soils, the unconfined compressive strength is reduced greatly when the soils are tested after remolding without any change in their moisture content. This property of clay soils is called sensitivity. The degree of sensitivity is defined as the ratio of the unconfined compressive strength in an undisturbed state to that in a remolded state. As ST increases, the soil sensitivity also increases. On the basis of their sensitivity, soils may be classified as given in the table. It ranges from insensitive to very quick state. Can you give any examples of soils based on the last mentioned classification? Yes, of course. Two remarkable examples are expansive soils and quick clays. Expansive soils can swell a lot when they absorb water and shrink when they dry out. This ongoing change in soil volume can cause buildings standing on the soil to move unevenly and crack. Quick clays are originally deposited in marine environment and they have a very delicate structure such as house of cards. When they are disturbed, they can lose a great portion of their strength and behave like a liquid and cause significant geotechnical problems, including landslide. Quick clays are only found in northern countries such as Russia, Canada, Norway, Sweden, Finland, and Alaska. Here you have a practical example to better understand the procedure for unified soil classification system. The laboratory test results of dormitory building site are reported as follows. In the table, you have information about company, boring, as well as sample identification. In the first column, you have also sieve nose. In the second column, the openings corresponding to each sieve and the percentages passing each sieve as a result of sieve analysis. In addition, several test results carried on the sample are also given. They are liquid limit, plastic limit, moisture content, unit weight of soil, and the specific gravity. It is noted that the sample is oven dried and dry sieved. Now then, you are asked to classify the soil regarding the unified soil classification system. From the laboratory test results, we have the percentage passing no 200 sieve, liquid limit, and plastic limit. In the first step, we need to select the related part of Unified Soil Classification System chart. Since the percent passing no 200 sieve is more than 50%, we now need to check whether the liquid limit is greater than 50% or not. Liquid limit is 67, so it is more than 50%. From here, We move to third column, where we need to check whether the plasticity index is above A line or not. To find out this, we need to calculate PI value, which is the difference between liquid limit and plastic limit. Now, we have liquid limit and plasticity index. Now, we need plasticity chart to determine whether PI value is above the A line or below that. On the plasticity chart, we mark plasticity index and liquid limit. The intersection point defines that PI value is above A line. Now, in the final stage, we need to classify soil accordingly. The USCS symbol for the soil is CH with group names defined as fat clay, in other words, high plasticity clay. Can we also classify the soil based on the liquidity index and activity? Yes, of course. Given are the liquid limit, plastic limit, natural water content, and clay fraction. These are all from laboratory tests. Now, we know that plasticity index is the difference between liquid limit and plastic limit. Remembering the equation for liquidity index and putting all the noun values in their places, we figure out Li value as 1.3. Referring to the related table, we can classify soil as viscous liquid if sheared, since Li value is greater than 1. Similarly, putting the noun values in activity equation, we can find out activity value as 0.45. Going to the related table, we can define the classification of the soil, which is inactive clay, since the activity is less than 0.75. Now let us review what we have learned so far. The Unified Soil Classification System classifies soils into what? Yes, you got it. Two main categories. The second question, which statement is not correct? Please read the options carefully. No, it is not. It is not. It has to be C. Soil classification is based on the soil particle size. This statement is not correct because soil classification is not only based on the soil particle size, but also the plasticity. The third question, which of the following items is not used with fine-grained soils? Easy for you. Yes, the answer is B, relative density. You don't know what the relative density is yet, don't you? So the answer is very easy then. Which of the following clay minerals is usually associated with the greatest liquid limit? Yes, the answer is D, Montmorillonite. Good. Now the fifth question, the related laboratory tests on a soil sample gave the following results. gravel fraction 41%, sand fraction 25%, silt fraction 27%, and clay fraction 7%. Liquid limit is 26%, plastic limit is 17%, and natural content of soil subjected to those tests is 20%. Classify the soil based on the activity. Remember the activity equation, which is very simple, a ratio between plasticity index and the clay fraction. Figure out, compare your result with those listed in the related table and classify the soil. What? Yes, the answer is C, active clay. Good for you. Here you have another question. Which soil has the highest clay fraction? Shall we answer this question together? Okay then. What we know is clay soils are those whose particles are less than 2 micron. So we need to mark 2 micron on the horizontal axis of this figure. It is somewhere here. And then draw a line upwards until it intersects the curves. The curves for soil 3 and soil 1 are excluded because they fail to reach to this point. Projections of the intersection points of these curves on the vertical axis will give us the percentage passing for each one. So the percentage passing is 10% for soil 2, and it is over 30% for soil 4. Therefore, soil 4 has the highest clay fraction. Accordingly, the answer should be D. Question 7. Which soil has the highest gravel fraction? Now, following the same procedure explained earlier, you can easily find out which soil has the highest gravel fraction. I'm waiting for your answer. No, be careful. Yes, it is A. Soil 1 has the greatest or highest gravel fraction. Well done. Question 8. Which soil can be classified as poorly graded? Let us give you a clue. Poorly graded means uniformly graded. No, it is not. It is not. The answer is C. Soil 3 is poorly graded because soil 3 has more or less the same size of soil particles, and therefore it is named as poorly graded, in other words, uniformly graded soil. Question 9. What clay has the greatest liquid limit? Yes, you are right. It is C. CH, highly plastic clay. And the 10th question. If liquidity index is nil, in other words, is zero. The natural water content of plastic soil is equal to its what? Check out your notes and find the related equation for liquidity index. Then figure out what it is. You must be kidding, man. No, it is not. It is B, plastic limit. And the final question, what statement of the following is wrong? Be careful. Try to understand what you read. Who said that? Can you repeat, please? You got it right. Congratulations. The answer is D. The more active the fine-grained soil is, the less problems it will likely cause. So, folks, that's the end of our lecture. I appreciate your attention and look forward to seeing you in the next lecture.